Hi there, this is Ticky Thakkar. I'm from uh, TII, which is Technology Innovation Institute, and I'm the chief researcher in the Secure Systems Research Center. And I'm going to talk today about the Zero Trust autonomous systems. Let's see, so we just get this back here. I hope you can see my slide, and hopefully you can follow what I'm saying. So the agenda today is that I'm going to talk to you about what TII is and Secure Systems Research Center, and then talk about the secure autonomous systems and then secure drone systems. Okay. So TII is really an applied research arm of what's called the Advanced Technology Research Council. This is part of the UAE sponsored, um, government sponsored research group. And there are two pieces to that research group. There's the Technology Innovation Institute, and then there's something called Aspire, which is basically drives the program management of some of the big events we do with the ecosystems and kind of drives the programs transfer of the technology from TII to industry. And so there are two pieces that are enabled. So what's the unique piece about TII? TII foremost is an applied research group. TII is being centered around 7 areas of research, and the whole purpose of creating TII was to have the research be driven into industry and the ecosystem in UAE. And so we are a world-class organization focused on some key areas that we want to work with the local and external universities, and you'll see that we have a lot of universities that are kind of part of our partners. So the 7 centers of this TII are the Quantum Research, the Autonomous Robotics Research Center, the Cryptographic Research Center, Advanced Material Research Center, the Digital Security Research Center, Directed Energy Research Center, and then Secure Systems Research Center. And the key differences between, as you'll see, there are a number of things mentioned here: cryptography, digital research, security research center. Cryptography is focused on really the cryptographic creation of algorithms. The secure systems, on the other hand, is using some of the technologies that are created by the cryptography team. Likewise, digital security, is focused on the tools that enable better secure development. And so again, we are kind of a customer of that as well. And I'll talk about what we do in Secure Systems Research Center. So in Secure Systems Research Center really is very, very simple. It's to really drive zero trust, end-to-end security and resilience in the cyber physical and the autonomous systems that ensure safety and enrich lives in UAE and worldwide. Those are many words. And what I want to kind of focus, first of all, is as you look at the systems today in smart cities, there are a lot of edge devices connected to physical things. So physical is connected to digital, and then they are connected to a backbone of whether it's in the cloud or a private cloud or a public cloud environment. And these systems, currently are mostly semi-autonomous systems as such. And what we were looking and what we are trying to do is to really drive an environment where you're going to have, millions of edge points connected to a digital backbone. And what we want to do is that digital backbone will be autonomously driving and controlling the billions of devices that it's connected to. And we want to create a secure and resilience, security and resilience in that kind of environment as such. And so that's our key focus in what we are trying to drive here. And there's set of number of tools that we use. So we do hardware hardening, that includes tamper resistance, alternative channels for resilience, software hardening against malware. Um, and again, we look at the operating system, the applications, and the cloud, maintaining system integrity and preventing data exfiltration, and then really looking at the communication hardening protocols, and providing much more resilience in the communications that we manage. At the platform level, we have different kinds of platforms. We have the cloud infrastructure, we have the client platforms, which includes autonomous vehicles or smartphones, and really looking at the communication, secure and resilient communication that connects those two platforms together. If I look at what, our projects, we kind of divide them into really secure technologies and a couple of other projects that we apply the technologies to. So in terms of secure technologies, we have research going on in secure OS, maintaining system integrity, um, preventing data exfiltration. Again, we use ML for some of those capabilities. Secure connectivity, and mesh is one of our core capabilities that we are trying to drive. As you'll see in the systems we need, mesh gives us a resilience that's missing in all the other environments. And then really drive secure communication protocols, virtualization, either on the device or in the cloud, and then driving secure silicon technologies. And we're looking at basically driving RISC-V as our kind of foundation, and we'll talk a little bit about that, the SoC and the platform. And then finally, the secure applications. So these are kind of our foundational technologies that we are driving. On the in the project side, we have two projects. One is secure smartphone, the other one is secure autonomous systems. In terms of the secure smartphone, we're looking at the good, better, best models. So can we do something that combines with an Android phone, but protects your data into a secure component? We call it secure sleeve, and this could be with or without its own special communications like the mesh network capabilities. And we also look at secure thin phones, which kind of provides the best level of kind of protection because it's got its own phone hardware, it's got its own operating system, the applications. And the reason we call it thin is we don't want to put a large operating system like Android there because it increases the vulnerability areas. And then as Android evolves, we have to keep patching it in terms of the security hardening and all of those things. So we're basically driving a thin phone with a separate, with a secure OS, secure applications, secure communications capability. And then finally, app virtualization on the cloud, which is pretty much, works just what it says is the app is running on the cloud and only the rendering, is happening on the phone. In the first and the third cases, you have basically the vulnerabilities are that your keystrokes may be able to be captured on a standard phone. The best option there is secure thin phone, where none of those things will be captured, by because the applications are all secured, and the operating system is secured, the hardware is secured, and so there's no malware running on that phone. And finally, and the bulk of this discussion today is on the secure autonomous systems. To basically model a smart city or a set of autonomous systems, what we created here was we're looking at a secure cloud-based autonomous system, and and the secure autonomous robots, which could be drones, it could be it could be cars, and then really the one of the other things we're doing is also looking at a secure flight controller SOCN platform. So our research is driven by use cases and zero trust architecture. When I go into details about that, we're using open source based components, modular architecture. We truly believe that security comes through transparency and not through secrecy or obfuscation. And we want to contribute and drive community to develop zero trust secure systems, because this has to be foundation of any systems we develop. In terms of zero trust architecture, I think Forrester put it very well. Zero trust architecture is a framework built around concept of never trust, always verify, and assume that there will be a bridge. And this is kind of the fundamental of the notion that goes behind creating a zero trust framework. And it's very well articulated by Martin Dixon, who is one of my previous colleagues at Intel. And it comes into a number of core capabilities. Fail safely and securely. What that means is when you have an error, whether it's in hardware or software, you don't want to leave things around that will compromise the integrity of what you're trying to drive. Complete mediation. You want to make sure that the access that you're driving has the right level of authority, and in case you want to build multiple walls to make sure that the access is verified in terms of security, and making sure that it's available, it's only accessible given the right set of permissions. And then separation of duty, because a lot of times people combine many functions together, and Intel architecture, for example, tries to separate the processor from doing the secure execution through something called SGX. Same thing goes for ARM. They try to do it through trusted execution. The key thing is that you want to separate security functions from others so that you don't compromise the integrity of the security functions that may happen, or may leave something residue around that might be able to be captured and be able to give some idea of what was happening while you were doing secure execution. And then really rule of least privilege. You want to minimize the creep in the the privilege levels inside a processor or inside software. And this basically goes to driving to simpler architectures, keeping the security mechanisms easy to use. So these are kind of the founding capabilities of what we want in zero trust architecture. So what is the secure autonomous systems that we're building? And when people talk about autonomous things and drones, they immediately think about drones as being autonomous devices. Yes, that's given. For us, when you make sure that the drone is asked to go from point A to point B, it avoids obstacles and making sure that it doesn't crash, etc., into some of the on the path, and it avoids obstacles to get to its work done. When we talk about the autonomous system here, we talk about a system that is autonomously managing autonomous devices. So we talk about a cloud-based system that is managing a swarm of drones. The drones are connected, in kind of different layers. So there's a fog layer, there's an edge layer, and the fog layer, just like in fog computing, if the connectivity disappears to the cloud, what you have is the connectivity, the fog layer can manage and complete the mission by itself. The same thing goes down a layer down to the edge devices as well. And the goal here is that the system will be driven from the cloud we'll have an operator basically reviewing what the system is doing, but it manages by itself. And this is a kind of um, uh, an example of a system that could be managing smart cities, managing traffic lights in the cities, managing, airports, etc. So this is just an approximation of what we are trying to drive in terms of an autonomous systems. The key things is that only the edge and the end-to-end security and resilience makes this, following use cases possible. Secure delivery, whether it's the vaccines in, the current time that we have with COVID-19, habitat monitoring, national parks monitoring, making sure that the the habitat is kept safe, and also the people are kept safe from the some of the animals that could encroach into farmland, etc. Infrastructure monitoring could be ports, want to see what's going on in the ports. There's a lot of activity happening, and this allows, again, an autonomous system to drive that. And finally, emergency response could be fire, could be earthquake, could be lots of different things that could happen. And you want the autonomous systems to be there on, available before any of the current, emergency response systems are there. Essentially helping the rescue teams to get more information of what's going on, etc. So when we look at these class of systems, we see lots of problems. And so what we have here is a single drone architecture here. And what you see in the single drone, architecture is DX4 based thing, a mission computer. Basically, if you look at the current level of systems, and again, we're not talking about, tomorrow somebody is going to have a better chip and going to do better things in terms of, providing process isolation, etc. If we look at it today, there's no process isolation, absent hardware reset, no mitigation of any of the hardware exploits, whether it's Wi-Fi, Bluetooth, physical access to the ports, redundancy is absent. And then there's physical access to the, the chips. And at the next layer up, you could be injecting malware to the firmware. You could be, sending exfiltration. And by the way, we've demonstrated some of the things in our own labs. So it's not like these are hypotheticals. We can actually show you that these things occur, and these things are very much, vulnerabilities in the platform. And at the system level, there is lots of other, potential issues as well. There could be kind of, you see a little evil drone here, but it could be an alien drone, infiltrating your swarm, and or protected space. There could be a link lost. There could be adversarial mission uploaded into the system. So there could be lots of things that could, potentially go wrong in this class of systems. And we want to address these things as we go forward. So we built our own Zero Trust end-to-end secure and resilient autonomous systems. It's a cloud-based systems, as you can see here. We're providing secure provisioning, secure operations, secure analysis, that could be telemetry or application. And then we want to also go into and look at secure airspace management. As these systems, work with the current airspace, ATS systems, how do we manage these class of drones and secure communication so that it's not spoofed, etc., between the airspace management and the cloud-based systems that you see here. The platform, clearly we want to drive secure drone connectivity. As I said, mesh is a critical thing because it gives us resilience, and it also cuts down the amount of traffic going back to the cloud. We're looking at the ML-based security and resilience. We're looking at, monitoring the drone, and seeing any kind of suspicious activity on the drone, by using ML can give us a better security and resilience. And then really working, and that's why we are here and we're supporting Drone Code, is we want to work with the ecosystem. We want to create a secure ecosystem, whether it's PX4, NUTX, ROS2, RIS5, Linux. We want to contribute to make sure that that we can have, all of us can share a secure components, secure autonomous systems as such. If you look at where we are today, we kind of built a software stack which you guys have seen, and much more familiar. We're using currently flight controller that's PX4 version. I think we're using version 4, moving to version 5, etc. And we're also using the Intel Extreme as our mission computer. And then we have a talk later on in the presentation given by Yuka, and Yuka is going to talk about what are the things we've done to date to make the PX4 security improvements. And Yuka is leading the security work group, part of the Drone Code organization. And so far, we've made the following changes. We've enabled memory protections in implementation that includes existing flight controllers. We've defined and implemented baseline crypto interfaces into the PX4. We've defined and enabled signed boot support and device that can be locked only to run signed firmware. We've implemented flight log file encryption on PX4, again protecting data in case the drone falls into wrong hands. And then we are enhancing these functions on the next set of hardware, which is based on RIS5. And if you look at RIS5, what are we doing? We have basically a 3-year program with multiple partners with following activity. Currently, we're building a RIS5 based solution just using off-the-shelf components so we can port the software stack. And this work has already started, and Yuka will talk a little bit about that in his presentation later today. We're also building a secure, RIS5 based SoC and platform to replace, the COTS solution, because we wanted to see more fundamental, ground up security as such in the system. And then really we're designing at the same time a RIS5 architecture. We're doing some of the more interesting extensions again with the RIS5. It's again done on an FPGA with the Hyper-V, which is the extension to support hypervisor, better hardware support for hypervisor, IO MMU. These are going to give us capabilities similar to some of the things you see in Trust Zone and some of the other capabilities that are in the Intel architecture, and then really drive some of the crypto ISA extensions, again, part of the open ecosystem. Again, we want the ecosystem to use these things. We want to work with the ecosystem to make this thing happen. And as you see, we have really great set of partners. We've started the work here really to define the Xero Truss drone system. We're working again with the drone ecosystem, as I mentioned, from secure autonomous systems, platforms, ML, secure wireless, and secure technologies. And we have a strong research community, with over 14 universities that is funded by our research team to support each of these areas. And we will be talking about those, in a separate talk later. And then finally, what I want to leave you all with today is how can we make this, Zero Trust drone architecture solution even more resilient? And so we want to look at securing runtime assurance, full triple redundancy for flight controllers. We want to have a very well-defined secure connectivities to the peripherals, and there's some work, in our research team and partners that are driving that. And finally, we also want to work with the manufacturers of whether it's gimbals, motors, sensors, battery, to really secure the hardware and software for the peripherals. So thank you very much. I'm going to stop here and take some Q&A or chat, whichever you prefer to take. Okay, let's see. Hey, I've been quiet, but I'm answering a lot of the questions on the Q&A, and I hope that's coming across well. Um, and and the program people let me know when my session is done, so I don't go over. Thank you.